So in this course, we will consider various abstract data types and how to implement them using different data structures. The data structure you choose will have implications on the time your data type takes to perform certain operations, and it's going to have implications on the space required to implement it. One of the most studied abstract data types is the list. The benefit of creating an ADT is that a client using your ADT will not have to worry about how it's implemented. To design a good ADT, you have to have a clear interface and a good implementation where it's optimized for its use case. A clear interface means that the clients know exactly what they can do with it. All right, so let's define the list interface, shall we? So we want this list ADT to have the following operations. Check if the list is empty or not. Insert an element into the list in front, back, or any position without overriding the other elements. Remove an element from the list from any position. Read and modify an element at a specific position. And finally, search the list for a specific element. One characteristic of a list is that it's ordered. So keeping the original sequencing is important. So that means if I had a list with elements 1, 2, 3, that's not equal to a list with elements 2, 3, 1. Some other data types like the set, sequencing does not matter. So for a set with elements 1, 2, 3, it's equal to a set with elements 2, 3, 1, since the order doesn't matter. You'll also learn how to implement a set in the future. Okay, now that you know what a list should do, it's time to implement it with core data structures. So in computer science, every abstract data types are implemented with a combination of the following core data structures, which we'll all learn. Primitives, like for example an integer, structures, like for example a node, arrays, linked lists, trees, and graphs. Today we'll be talking about the array in the context of implementing our list. The other implementation is using a linked list, which we'll talk about in the next lesson. So what exactly is an array? Unfortunately, if you came from a high-level language like Python, all of the data structures that you use, like the list in Python, is actually an abstract data type that the creators of Python created for you to use directly. Arrays are actually way more primitive than that. An array is a data structure that contains a fixed number of elements that all have the same type. So for example, if I initialize the list int myArray, then this is what happens in memory. If I want to access the third element, then I can specify the index that I want to read, and that will get me the value 7. What happens when I want to extend my array? What if I want 5 elements instead? You might think you can just allocate another block next to your last element, but you can't do that because you can't guarantee that your program is not using those bytes of memory for something else. Let's look at another example. This is what your memory looked like before initializing your array. And when you initialized it, it was a perfect fit. So you put your array right in there. Well, if you want to extend your array, tough luck. The only way to do that is to request another block of memory that can fit your 5 integers, and then copy what you had from your old array into your new array, and then telling your program that you don't need that old block of 4 integers anymore, aka freeing the memory. Okay, now let's go back to the list ADT. Let's brainstorm some ideas on how we can implement this. Okay, let's just implement it using a huge array, so we have enough space for any future element inserted. Let's use 10,000 for now. All right, so we have int myArray. All right, let's look at the requirements again. With what we have so far, we can't actually check if the list is empty or not. We just reserved 10,000 blocks of contiguous memory, so we don't even know where our array starts or ends. So let's add one more variable called length, which tracks how many elements our list has. So every time we insert an element in our list, what we can do is we can just add the element into our array and then add 1 to our length to track it. So if length was equal to 0, we know it's empty. All right, so first point checked. Okay, now insert an element to the front, back, or any other position of the list without overwriting the other elements. So in our case, front is the first element you inserted and back is the last element you inserted. Let's insert a few elements using our trick with the length. So we can just use the length as our index to insert the element to the back of our list. We insert to the back of 4, we insert a 1, we insert a 6. Inserting to the back of the list seems pretty easy and straightforward. So let's do a few more. We insert 2 and then we insert 5. Okay, what about inserting in front? We can do that, but we'll just have to move all the other elements one at a time. 5 goes here, 2 goes here, 6 goes here, 1 goes here, and 4 goes here. And then finally, we add our new element 9 in front. That's a lot more work than insert back. This is a good opportunity to talk about time complexity. What do you think is the time complexity for inserting an element into the back of your list with your array implementation? It's O of 1, because all you need to do is assign the value to my array and then put length into the index and then increment the length. No matter how long your list is, it's just 2 operations, hence constant time. What about insert front? For simplicity's sake, let's just assume shifting it only takes 1 operation. You have to shift every single element, so it'll take n shifts, where n is the number of elements in your array. Hence, this is an O of n operation. All right, what about inserting at a specific position, like inserting an element 8 at position 2? Very similar to inserting in front, we just have to move all these elements from the back until position 2. And then we can add the element 8 in position 2. This is an O of n operation because in the worst case, you choose position 0. Okay, so far so good. Now what about removing elements? So let's remove the element in position 0. Again, very similar to inserting in front, but instead we start from the front of the list. We don't need the element in position 0 anymore, so we just shift every element to the left like so. Again, this is an O of n operation. Okay, what about if I remove the last element in position 5? That one is easy. I don't need to shift at all, so this is an O of 1 operation. Read and modify elements at a position, that's an O of 1 operation. Because it is an array, I can just access the index and return the value. Or if I want to modify it, I can just overwrite the value. No need to shift anything. This is the array's specialty. What about searching for an element? This is also an O of n operation because you'll just have to look through your whole array. Each time you look at an element in your array, that's considered as one operation. And in the worst case, you have n elements to look through. So it seems like we just needed an array and an integer variable to implement our list. But there's one thing we forgot about. What if we have more than 10,000 elements? Maybe start with a bigger array? So what happens when we exceed that too? Will we be able to solve this problem using arrays? Stay tuned on the next episode to find out. Spoilers, yes we can, using dynamic arrays.